Yes. Yep.
maybe?
Yes, yes.
Oh, I do got it. So here you see there's all sorts of structuring. It's not just a smooth atmosphere of the sun streaming away from the sun. It's structured by the sun's magnetic field. Because, of course, the sun's atmosphere is so hot that it's not a neutral atmosphere. The electrons have been stripped away from the nuclei, and you're left with a plasma. So charged nuclei, positive charged nuclei, and electrons, which are governed by magnetic fields. They move at the whims of this local structure and strength of the magnetic field, which is what you're seeing when you see the sun in eclipse and you see all that nice structuring features. Even this picture of the sun is not a complete picture because, of course, the sun has a solar cycle and goes through tumultuous active phases when the sunspot number is high. And during those times, we have a larger number of solar flares, coronal mass ejections, and other extra energetic releases of plasma and magnetic flux from the sun that then migrate out, populating our near space environment. By the time that solar wind reaches the Earth, it's what we consider the vacuum of space. But as a space plasma physicist, I'm like, wow, that dense solar wind is all of 5 particles per cubic centimeter by the time it reaches Earth's distance from the sun. Nothing slows it down. It's moving at 400 or so kilometers a second, give or take 100 kilometers a second for activity. And that speed is actually supersonic and super alphanic, which means it's moving faster than magnetic waves and pressure waves can propagate through the medium. And the magnetic field from the sun that it carries with it, that it's threaded with, because of the fact that it's a plasma, is about 5 nanoteslas. For scale, we're currently sitting at around 31,000 nanotesla at the surface of the Earth. You all might be in a slightly weaker field than I am because of magnetic latitude, but roughly 31,000 nanotesla. So that's the solar wind, and it streams away from the sun. And what does it do when it gets to the Earth? It slams into an obstruction because it's moving faster than the speed of sound and faster than the speed magnetic waves can propagate through this magnetized plasma. And so it creates a shock wave upstream of the Earth because of feeling the Earth's magnetic field. And this little animation from the NASA Conceptual Image Lab is really nice because it shows that solar wind smacking into this magnetic obstruction, creating a shock. And then through the wonders of magnetic reconnection, we see a reconfiguration of the Earth's magnetic field due to that magnetized solar wind. And what that does is it perturbs the magnetic environment around the Earth, accelerates plasma, and leads to phenomena that are maybe more near and dear to our hearts, phenomena like the aurora. And I don't know if any of you have seen the aurora. I did not see it while I was living in Pennsylvania, I'll be quite honest. But I have had the pleasure of seeing it from airplane rides and also in Iceland when I was there for a conference. And it's phenomenal. Of course, it's one of the most beautiful and striking things I've ever had the pleasure of seeing in person. And all of that is to say that when we look up in the night sky and we see phenomena such as the aurora, what we're really capturing is an expression of the dynamic environment around the Earth that's generated by the interaction of the solar wind and the Earth's own magnetic field. And so, sorry, it's a nice video, but we won't watch it again. If we look at it as a template of understanding planetary magnetic fields and solar wind, stellar wind interactions in general, we come up with this cartoon, which is helpful and indicative of the most well-studied magnetospheric interaction we have, our own. And we've been studying it from ground-based observations, from orbiting satellite observations, from satellites sitting at various points observing the solar wind coming at us, not to mention orbiting cameras, ultraviolet cameras, studying the aurora from a global perspective while in orbit, as opposed to the visual spectrum that we're able to observe from the ground. And so we have this cartoon, and I'll just point out a few features so that we kind of hold them in our minds as we start moving to other planets and seeing similarities and differences. We have this bow shock, this nice parabolic curved structure, which is, of course, in 3D, not just this 2D slice. And inside that bow shock, which is where the solar wind runs into this obstacle and has to be diverted around it, essentially. We have this shocked plasma and magnetic field region called the magnetosheath, where all that dynamic speed from the solar wind is jumps over that shock and is translated into thermal energy. So very hot, turbulent plasma in the magnetosheath. And then we have this purple boundary called the magnetopause. And this is probably my favorite boundary because it is a dynamic pressure boundary. And the way we like to think about it is the solar wind has a dynamic pressure because it's mass density times velocity squared in fluid dynamics. That gives us a dynamic pressure. And the Earth's magnetic field, B squared over 2 mu naught, gives us a magnetic pressure to fend off that dynamic pressure. So this purple boundary moves in and out depending on how strong or weak the solar wind is. When the solar wind is weaker, Earth's magnetic pressure wins and it expands out. And when the solar wind is being very tumultuous, very active because of a coronal mass ejection or some other perturbation to the average flow, it compresses our magnetopause in, because then the dynamic pressure of the solar wind is dominating the region around the Earth's magnetosphere. So this is something that we study a lot as space physicists because we have a lot of space-based assets, right? We care about all our satellites orbiting at geosynchronous orbit at 6 Earth radii. We care about our telecommunications assets and all sorts of climate satellites and the whole retinue of satellites that we have in orbit. And understanding the dynamic variability of this environment around our Earth as driven by the solar wind and modulated by our own Earth's magnetic field is an important component to protecting those space-based assets. And that's really why we have the whole field of space physics, was to understand and protect our satellites for communications. And so if we then take a jump out and think about another extreme end member, we have the Earth, which is really a battle between the solar wind and our Earth's magnetic field. And then we move all the way out to Jupiter at 5 AU. And Jupiter is a different bag of chips completely because it has a really, really strong magnetic field, incredibly strong magnetic field, much stronger than the Earth's magnetic field. It's a larger body as well. And it rotates very quickly on the order of 10 hours per day. A 10-hour rotation period makes up its day. And just for good measure, we have the most volcanically active object in the solar system residing inside that magnetosphere, which is Io, the innermost of the Galilean moons of Jupiter. And it's spewing out literally a ton of material per second, a ton of sulfur dioxide per second from all its volcanic activity that pumps into, if you will, Jupiter's magnetosphere. It becomes ionized very quickly because Jupiter's magnetosphere is a high radiation environment. And that is essentially almost like pumping up a balloon, except instead of a balloon, it's a magnetic balloon. And instead of helium, we're filling it with plasma. So that adds a plasma pressure inside the magnetosphere. And what we call Jupiter is really a rotationally driven magnetosphere because of the fact that it has an intense interior plasma source and it's rotating very quickly. And to be quite frank, Jupiter doesn't care if the solar wind is being tumultuous and active or not, because by the time the solar wind gets all the way out to 5 AU, it's pretty diffuse. It's even more diffuse than the 5 particles per cubic centimeter at the Earth. Right? It's still moving at 400 kilometers a second, but it's maybe down to 2 particles per cubic centimeter or 1 particle per cubic centimeter by the time it gets all the way out to Jupiter, because it's radially propagating out from the sun and expanding into space. So at one end, we have the Earth's magnetosphere, which is solar wind driven. All its dynamics are because of changes in the solar wind. Then we get to Jupiter, which we would call internally or rotationally driven because of the interior plasma sources and the strong magnetic field that's rapidly rotating. And then we have other planets that are not really on the spectrum, but more complicated. Oh, is there a question in the chat? I can't open the chat and share my screen at the same time. So if there is a question, I hope that maybe Dawn might be able to catch it for me and interrupt me.
There's one question.
Uh-oh. I can't hear anyone if you're saying the question.
Yeah, I had to come through I have 2 computers going. If I open if I
Oh,
unmute the other one, we have a terrible echo. So
oh yes.
question was, how does the moon affect the magnetosphere?
How does our moon affect the magnetosphere?
It says the moon. I assume they mean our moon. Yeah.
Sorry, as a planetary scientist, the moon is vague, but I believe you that you meant our moon.
They must have met our moon, yeah.
Yeah, well, for the most part, our moon orbits a bit farther out than our magnetosphere extends on the day side. So our magnetosphere, that bow shock, resides usually around 10 Earth radii out. So if the moon is orbiting in between us and the sun, it's outside of our magnetospheric boundary. When it sweeps around to the backside, one of the details I kind of brushed over was the fact that on the night side, our magnetosphere is stretched out into an elongated tail. And I teach a whole space physics class as to why that tail is so elongated and how it can be sustained for hundreds of radii away from the planet, even though a dipole field would tell you it falls off as 1/r². But the truth of the matter is, when the moon orbits around the Earth, it does pass through our magneto tail. In fact, it probably is. It's more that the moon is influenced by our magnetosphere than the other way around, because our magnetosphere is ejecting plasma sourced from our ionosphere. So a lot of oxygen plus and H plus from our upper atmosphere ends up being swept down tail and actually collides with the surface of the moon when it's orbiting in its orbital path through our tail, through our wake, as it were, in the solar wind. So the moon doesn't affect our magnetosphere too much, it turns out, but it does in fact pass through the back end of our magnetosphere. So I hope that answers that question. So if we now move on to Uranus and Neptune and think about what do we even know about Uranus and Neptune? They're really far out there. Uranus is at 19.2 AU on average. Of course, Uranus has an elliptical orbit, so it's more like anywhere between 18 and 20 AU in distance, depending on what season it is and where it is in its orbit. And Neptune is all the way out at 30 astronomical units, so 30 times further out than we are from the sun. And so these planets pose many interesting questions about that solar wind magnetosphere interaction. First off, do they have magnetic fields? I mean, intuitively, we'd think, sure, why not? Earth has a magnetic field, Jupiter has a magnetic field, Saturn has a magnetic field. Why wouldn't the ice giants have magnetic fields? But the truth of the matter is, we've only visited either of these planets once with a very rapid flyby from the Voyager 2 spacecraft, which is beautifully pictured here. I love the Voyager spacecraft. It's honestly what got me into planetary science, because I was so inspired by these flybys as I was moving my way through elementary and middle school, and all the beautiful images that were in the Reader's Digest magazine that I had at home. And I thought, my gosh, we see all this amazing stuff from this one tiny spacecraft sending this information back over millions and millions of kilometers, which I couldn't even really get my head around at that age. But this is Voyager, and it flew, the Voyagers launched in August of 1977. And well, Voyager 2 launched in August of 1977. Voyager 1 launched in September of 1977. Voyager 1, we really wanted to get a close look at Titan. And because of that, it meant when we went past Saturn, all the planets were aligned, hence why we had the Voyagers. We wanted to do the grand tour of the solar system using a newly exploited ability of gravitational assists, meaning using the gravity of one planet to help accelerate us and move us on to the next planet. And all the planets were in a convenient orientation so that we could do that and fly by all 4 of the outer planets. Except there was this nagging feeling that we really wanted to take a close look at Titan. And that's because the Pioneer missions that went through Saturn saw Titan as a moon with a thick atmosphere. And we said, oh my gosh, we need to take a closer look at Titan. We need to look and see if we can see beneath the haze at what this thick atmosphered moon in the outer solar system is doing. And so Voyager 1 was deflected off of its path, as it were, because we wanted to do a close look at Titan. So it got deflected by Titan and then kind of took a trajectory off of the ecliptic plane where the planets reside and didn't get to visit Uranus and Neptune. Voyager 2, however, used that gravity assist from Saturn and kept going on to fly past Uranus. Just a single flyby, just a snapshot, a couple of hours it spent in the near space environment of Uranus, and then go on and several years later, almost 3 years later, fly past Neptune as well. So it's a beautiful story. The Voyager missions are some of my favorite of all time. this is the only time we've ever gotten a close-up look at Uranus or Neptune. They're far out. 19 and 30 AU means they don't reflect a lot of light. For any of you who've tried to look at it with a telescope in your backyard, there's not a lot to see other than to see them and know that they're there. And even with Hubble Space Telescope, it's been challenging to gather a lot of information just telescopically, visually. In the ultraviolet, we've tried looking in the ultraviolet as well for aurora. They're just a bit far away for our resolving capability and the amount of light that they're bouncing back toward us. So it's tricky. And yet, even with this minimal amount of time that we've spent in their location, we learned so much. And it inspires us. It inspires us to go back. It inspires us to ask more questions. And I'll do a little bit of a quick tour of some of the data and the things we've learned and what people have been extrapolating from that data set, which is now decades old, to help formulate the questions that inspire us to go back. And so this was a bit of a passion project for the last 2 years. I was invited to help write the decadal strategy for planetary and astrobiology. That was a study commissioned by the national academies. And we spent about 1.5 years gathering information from the international community to figure out what are our highest priorities, science priorities for planetary exploration, and topping out the list for the next flagship mission. So after Clipper launches, after Mars sample return, the next one that we're going to start formulation for in 2024 will be Uranus orbiter and probe. So the planetary community viewed this minimal data set and all the work that's been done in the decades since then from comparative planetology and from other theoretical means to say our highest priority in planetary exploration is to go back to Uranus and study Uranus and its atmosphere and its magnetosphere and its icy moons to really solidify our understanding of this piece of our planetary neighborhood puzzle. And it helps us get to the questions of origins and evolution of our solar system and a slew of other questions as well. But I'm a magnetospheric scientist, so I want to go back and show you what Voyager saw. Because it's, in some ways, I mean, it depends on your perspective. Is it overwhelming or is it underwhelming? This is a line that represents the magnetic field that was measured as we flew by Voyager. And this is about 4-minute resolution, I believe, data. This is out in the solar wind. Again, 0.1 nanotesla. The solar wind is pretty meager out there in terms of magnetic field strength and even more meager in terms of density. And then we see this increase. And all of a sudden we cross, this BS is the bow shock, and then the magnetopause MP at Uranus. And then all this peak here, this rather smooth, beautiful looking peak that then comes back down, that's the magnetic field of Uranus. And we did a lot of analysis on that magnetic field to paint a picture of what Uranus's magnetic field is like. And then on the way out, we had a real field day in terms of what we observed. We kept seeing these dips happening as we thought, with our picture of the Earth's magnetic field in mind, that we were just going to be flying down the tail for a while. But in fact, we saw this really dynamic environment. We were crossing the magnetopause several times, crossing, it turns out, the plasma sheet several times, that plasma dense region in the center of the tail. And then we finally crossed the bow shock again several times on our way out. And so what did this mean? The mental gymnastics that went from taking what we thought we were going to see, which is this simple, like, okay, the flyby should go across the bow shock, across the magnetopause, but then all of a sudden inside the magnetic fields are going all different directions. And that was not what was expected. Especially when we had this nice, smooth canonical diagram of what a dipole magnetosphere at Earth looked like. And it turned out that Uranus was fantastically cooperative with us, because instead of having a nice rotation axis and magnetic axis that were perfectly aligned, and so our trajectory would have looked like this, like flying smoothly across one boundary and then out the other one, what we got was a geometric nightmare of having a rotation axis that was highly inclined, or strong obliquity, and a magnetic axis that was tilted significantly off of that. So basically the entire magnetosphere was tumbling around, And we got to sample a whole lot of it because of that as we were flying through on this singular trajectory. It kind of revealed itself from lots of different angles because of this complicated tumbling geometry. And what we've found, both at Uranus and at Neptune, is that the dipole tilt, the tilt of the magnetic axis relative to the rotation axis, were incredibly large for these planets. Almost 60 degrees for Uranus, almost 50 degrees for Neptune. What was confusing is that if you tried to stick a dipole on these, it made it look like they were offset from center by a significant fraction of the radius of the body. So a third of a Uranus radius off-centered, or more than half of a Neptune radius off-centered. Now, that doesn't really sit very well for most people because we think about how dynamos generate magnetic field, and it tends to be in these spherically concentric layers, like at the Earth, the liquid outer core is where our dynamo field is generated. And so it's really probably not appropriate to call these tilted and offset dipoles. What it really is that there's higher order magnetic moments, quadrupole moments, octupole moments that create the effect of seeing a highly off-centered, highly tilted dipole. And so if you think about, and again, the rotation axis for Uranus here, when we flew by Uranus, the rotation axis was almost pointed directly at the sun, right? Its solstice is rotation axis pointing at the sun, and then equinoxes, it's 90-degree off, but in the direction of motion around the sun. So completely different geometry for its seasons than what we have. And so if you were to think about what do we see at the surface of the Earth in terms of the radial magnetic field, we'd see the radial magnetic field going out of one hemisphere and into the other. That's what a dipole geometry gives us. And that's what we see here, radially out in one hemisphere and in the other. And that, if you trace that along a magnetic equipotential, you'd get a nice dipole field line from one hemisphere to the other. Uranus and Neptune, it's a completely different story. And this is, again, because of those higher order magnetic moment contributions, these quadrupole and octupole terms, making it a very complex and interesting geometry. And so there were so many questions about what this means. What does it mean for that standoff distance of the magnetopause if you can't just have this simple dipole field creating a magnetic pressure against the solar wind? What does it mean for the access of the solar wind through cusps and access of the solar wind to the polar regions if you have these higher order magnetic field components? And what does it mean for the magnetotail, that crazy magnetotail that had all those blips and bumps in it? If you have this tumbling magnetic field, then do you get a nice long stretched out tail with a centered high density peak? Or do you get something more twisted up and complicated? Can the structure even sustain itself at long distances when you have a complicated twisted geometry? And so all these questions came up just from a simple observation from a single flyby of a single spacecraft that was launched in the 70s and flew by in 86 or 89. But we had tools to think about these problems because we've studied Jupiter, like I said, lots of volcanic activity. We've studied Saturn, which has a reasonably high obliquity. 26 degrees is the tilt of its rotation axis, nothing compared to Uranus and Neptune, but still relatively tilted compared to the solar wind direction. And what that tilt does for Saturn, which by the way has a magnetic field that's almost perfectly aligned with its rotation axis. So at Saturn, the magnetic axis and rotation axis are barely separated by a degree. Oftentimes it's just said to be 0, but it might be a fraction of a degree, more likely. And what happens is the sun basically pushes up on the magnetic equator and creates a bowl shape at Saturn. And that bowl shape is seasonally sensitive because it depends on which way the rotation axis is pointing relative to the sun direction. And so we had this in our arsenal of pictures of what magnetospheres, how they respond to tilt and obliquity. But again, we have this spectrum of planets in terms of obliquity, so tilt relative to the solar wind direction that creates the seasons, and then magnetic axis tilt. And Neptune and Uranus are kind of outliers on this spectrum because they are so highly inclined and so have such high obliquities as well. And so if we just look at Uranus for a moment, and this is probably a good hint as to why the decadal survey chose Uranus as a high priority target, the obliquity is so large that the difference between equinox and solstice is dramatic, right? Solstice, the rotation axis is pointing at the sun. That's what we saw in 1986. Equinox, it's pointing perpendicular to the sun direction, but in the direction of its orbit. And somewhere in there, almost perpendicular to that axis, is the magnetic field axis. And be prepared for some dizzying graphic here. But this is equinox at Uranus. The sun is over here to that would be the left of the screen. The solar wind is propagating around to make the magnetic field interaction. But then the rotation axis of Uranus is pointing into the screen, and the magnetic field is tumbling around it. So every rotation, every day, you go pole on, equatorial on, pole on, equatorial on of the magnetic geometry relative to the solar wind direction. And this is just phenomenally different than anything we've ever observed at the Earth or Jupiter or Saturn. And the implications for the magnetosphere and the plasma in the magnetosphere are not insignificant and also almost hard to quantify, even with computer simulations and models like this one that my former student did. And so it has implications for like how that magnetopause and bow shock move in and out as the field is rotating relative to the direction of the solar wind. It has ramifications for plasma trapping because you don't have trapped closed field lines that are stable over long periods of time. And it has implications for what the tail looks like. This image movie cuts off before you get to see the full extent of the tail. So what's happening down tail with all this rotation? And what we find is, and the magnetotail has a helical structure, which I think probably this image best illustrates it, where blue is fields that are pointing away from the planet, in this case Uranus, and red, the fields are pointing at it. And as you move down tail, you kind of get this helical twisting of that magnetic field structure the further you get away from Uranus. And there have been some other simulations like this, one from Leah Graton and her group in France, which shows this kind of she basically sped up Uranus by a factor of 10 so she could get a nice long run of wrapping of that helical structure. It's pretty amazing. And it leads to, that plasma sheet, which on the Earth picture looks so smooth and nice and stretched out in the tail. And it leads to that being curved, which again, several people have modeled this out. They see a curvature there if you're looking at magnetic flux pointing toward and away from the planet, or if you're looking at that plasma sheet. These images here are just like taking a slice through the back, perpendicular slice, to see what that plasma sheet looks like. And it's completely curved. Which is, again, much different than we saw at the Earth, but really consistent with what they saw with the observations from Voyager, which again flew down tail and the whole tail spiraled and rotated underneath it. So a straight spacecraft trajectory basically was able to sample all the way around this helical tail because of that spiraling effect. And so if you put it in the perspective of the spacecraft and let the whole the magnetotail rotate around it, it looked like the spacecraft was doing a spiral, but really it's the magnetotail spiraling underneath the spacecraft as it flew away. So completely complicated magnetosphere. And we haven't even talked about the elephant in the room, which is, how does the solar wind even interact with this beast when it's 30 AU away? And the solar wind is so diffuse and so weak. At Earth, we see magnetic reconnection. It generates the aurora. It compresses the magnetosphere. Do Neptune and Uranus even sense that interaction in a strong way? Or is there a different process that couples the solar wind energy to these magnetic fields? And this has been a really interesting debate across the community, and it applies to exoplanets as well, as we're trying to understand those interactions with their stellar winds. On one end of the spectrum, we have this picture from Earth of global magnetic reconnection, where you get anti-parallel magnetic field lines along the magnetopause. That allows for the magnetic field to reconfigure itself, right? Like in that dynamic movie at the beginning of the talk, where energy is basically transmitted across this boundary through this reconnection process. So that's one way to look at it, as this. But what if it's a more viscous interaction? because it's not strong enough to generate magnetic reconnection. What does that look like? And what that looks like from a theoretical standpoint is Kelvin-Helmholtz instabilities, those same kind of curly Q clouds you might get where you have a two streams of wind going in opposite directions and creating vortices. You can get vortices as a mechanism for translating that energy across the boundary if you have a viscous interaction as opposed to a magnetic reconnection interaction where it's more explosive and dynamic and directly transmits that energy. And so there's been some theoretical work that looks at, well, how does the solar wind change characteristically with distance from the sun? So here's Mercury's location. Here's Earth at 1 AU. This is a log scale. Here's Jupiter at 5 AU, Saturn at close to 10, Uranus at close to 20, Neptune at close to 30. And again, the solar wind, nothing slows it down. So its speed stays at 400 kilometers a second, but it's becoming more diffuse as it goes out. So the density goes down. And the magnetic field strength also decreases, but not linearly. Or not even as 1/r squared, like the density might. And so what that means is characteristically, if we think about that alphane speed, like that magnetic sonic number of what drives the interaction, the further you go out in the solar system, the Mach number, the alphane speed, the alphane Mach number increases. And because the alphane speed is decreasing and the solar wind stays at 400 kilometers a second. So from a dynamic perspective, can we use information like the characteristics of the flow, kind of thinking back to our magnetohydrodynamics or our fluid dynamics theoretical framework, do we have a way of estimating where the transition occurs between global magnetic reconnection and Kelvin-Helmholtz instabilities, kind of a dynamic explosive interaction versus a more viscous shear interaction to translate energy across that boundary? And I don't know the answer yet. We don't know the answer yet. We have a theoretical framework that says closer to the sun, it should be more reconnection-y and less Kelvin-Helmholtz viscous-like. And the further away from the sun we get, it should be more viscous and less reconnection-y. But it's all normalized off of Earth, and we don't have critical values that tell us where this transition occurs. We just know what we've seen at Earth, what we've seen at Jupiter, what we've seen at Saturn, but we don't have a quantifiable transition or threshold under which we can say, yes, here is where the transition occurs between these two fundamentally different processes. So that's high on the list of what we'd like to know. And this is just if you were really wanting to get into the nitty-gritty details of the sonic speed and the sonic Mach number and the alphane Mach number, and what criteria you have to satisfy to allow magnetic reconnection to occur. Again, the geometry makes this a bit of a hot mess because Jupiter's magnetosphere is tumbling. So you don't even get the fundamental, like, do you have anti-parallel magnetic fields stably, even over the course of one day? Even over the course of one season, there's just so much changeover. Green means go, red means stop. Green means yes, maybe we can have reconnection. Red means definitely not. And this was just looking at a bunch of different geometries under which you can satisfy these two important conditions, one being the shear and one being diamagnetic drift, which is just another fancy way of enabling that reconnection to occur. And so you can get reconnection at Neptune under certain geometries and at certain times. And if you look at the percent of the time that you can get reconnection to occur across the boundary, it really depends on season, and it really depends on the phase of rotation. So it's not really predictable. It turns out it's very complicated, and we don't know the answer. And we want to go and figure out if we can answer that question, not just for Uranus and Neptune, but for planetary interactions in general with their stellar winds and how energy is critically transported across that protective boundary, that magnetopause shield in a magnetosphere. So that was the most of the more technical one. There's lots of other important questions we want to answer, though, like the importance of plasma sources. I talked about Earth's magnetosphere not having really an internal plasma source other than our own planet's atmosphere. And then we talk about Jupiter, which has the Io-plasma torus, which is a ton per second of material being pumped into the magnetic field. Saturn has the rings and Enceladus's plumes, which also pump out on the order of 800 kilograms per second of material into the magnetosphere. So Saturn also has a strong interior mass source. In terms of Uranus and Neptune, Uranus, we didn't really see anything. If anything, we saw the best case example of a vacuum magnetosphere we've ever detected. There's nothing in there, it appears, at least for most of it. But I'll get back to that. At Neptune, there was a hint of a Neptune source from Triton, the largest moon of Neptune, and Triton's ice geysers. And we think that that was the source because it appeared to be N+, nitrogen plus at Neptune. And that's what these were, just the density and the temperature of the different plasma species detected at Neptune as Voyager got close to Neptune and then as it flew away. And we did in fact see trace amounts, small amounts of N+, but again, actually less than we thought there would be for having such a large dynamic moon in its magnetosphere. And so if we look characteristically at the amount of plasma inside of each of these magnetospheres, we've got Jupiter here with a very localized, intense plasma source, that's Io. We've got Saturn with a diffuse source from the E ring and Enceladus's plumes, but it's diffuse because that material comes out cold and neutral, and it takes a while to get ionized. So it's distributed over radial distance away from Saturn. Magnetic L shell just means radial distance in the magnetic equator. And then at Neptune, we saw this hint in yellow of a very weak, I mean, they're all on the same scale here of particles per cubic centimeter per magnetic radius distance. And so there's probably something there from Neptune, from Triton. And Uranus, we just saw nothing. There was just no indication of a strong source or any source, which was somewhat surprising. There are lots of moons orbiting Uranus, but they don't seem to create much stable plasma. And I say stable with intent here because a lot of people with Io and Saturn talk about the longevity of plasma in the system. If you have a kilogram per second source, how long does it stick around, right? You can't just inflate that balloon up forever. It has to have a lifespan under which it eventually is lost from the system. So we talk about plasma longevity at Io, from Io's plasma source, or from Enceladus and the E ring at Saturn. But thinking about what it means for the fact that the magnetospheres of the ice giants are pretty much devoid of plasma was a bit strange. And so instead of longevity, I like to think about it as stability. And the reason for this is that with the complicated magnetic geometry of these tumbling magnetospheres, it turns out that we theoretically predict that the plasma doesn't stay stably trapped for very long. Even if Triton or other moons are creating a source of plasma, it just doesn't stick around. It doesn't have good plasma confinement because the geometry is not conducive for keeping plasma there for very long. That's the theory. That's the question that we hope to answer by actually having a bit more data from those systems. But there's a strong indication that it's the complex magnetic geometry and the high obliquity, the high tilt of the magnetic field and the obliquity at those moons or planets that's creating a very unstable magnetic environment for trapping plasma long term for the majority of the magnetosphere. Now you're going to call me a liar. You're going to say, I've just created this straw man and now I'm going to break it apart on you, because one place that we know at Earth is really, really good at trapping plasma are the radiation belts. And the radiation belts at Earth are an incredible discovery. They were our first scientific investigation and discovery when we became spacefaring. Explorer 1 and Explorer 3 did not just send up a basketball with an antenna on it that chirped. They sent up Geiger counters because we wanted to understand the radiation environment of space. We had all sorts of theories as to what was going on in space. We wanted to understand it better. And so they sent up Geiger counters and they detected not one, but two radiation trapping regions around the Earth. And these are what were later referred to or called the Van Allen radiation belts off of Richard Van Allen, who was the one who put those Geiger counters on Explorer 1 and Explorer 3. And we've studied these radiation belts extensively because radiation belts are, as their name indicates, a high radiation region of trapped plasma around the Earth that can negatively affect space-based assets and satellites and cause them to come down early and electronically fail. And so we want to study them. We want to understand the hazard that they pose not only to space-based electronics, but also to astronauts and other things. So we had a mission called the Van Allen Probes mission, or the Radiation Belt Storm Probes. And they spent years and years measuring our radiation belts to great effect. And our radiation belts are incredibly stable. they're sourced from the inner belts, are very stable. They're sourced from cosmic rays interacting with our own atmosphere, ionizing them, energizing them, and then they get trapped in the magnetic bottle that is the magnetic trap that our dipole field creates for them. The outer belts are much more sensitive to the solar wind and energization from solar wind and plasma wave processes that, again, pushes these energized particles to the inner magnetosphere, where they can then be stably trapped in a very magnetically stable, i.e. not affected much by the solar wind environment. So they stick around for quite a while. And that's our general canonical picture of radiation belts. This is a really pretty picture. The actual data of radiation belts looks very messy. It looks like this. And this is comparing the radiation belts of Earth, of Jupiter, of Uranus, of Neptune. Obviously, the Uranus and Neptune ones were observed by the single Voyager 2 flyby. And Jupiter and Earth are just representative images that were plotted on the same scale by Barry Mock and Nikki Fox. And so you're going to think that I told you a tall tale about Uranus and Neptune having empty magnetospheres, because here they have radiation belts. And where do those radiation belts come from, if not from plasma in the magnetosphere that's been accelerated and energized and trapped? So how can I in one breath say the magnetospheric geometry is really bad for trapping plasma, and then on the next slide show you that they have stable and intense radiation belts? It's a bit of a mystery, and it's a bit of a confusing point as to what's the source of these radiation belts. Where are they fed from? Is it from the atmosphere? Is it from magnetospheric dynamics? And then how are they stably trapped? If I've just told you that it's really hard to stably trap plasma because of the complex and ever-changing magnetic geometry. It is a real head scratcher, and it is a real conundrum, because it turns out that Uranus's radiation belts are really, really intense. They're not just a little bit intense, they're really intense. And there's a mismatch between the electron population and the proton population. And gosh, nature and plasma physics sure does not like that. We don't like mismatches between positive and negative charges. We like them to be quasi-neutral. At the end of the day, they all come from the same source. And so we want them to kind of sum up to one another at the end of the day. So these are another way of looking at those spectrum that are complicated to look at. And I don't know that these make it better, but they just kind of show the intensity in terms of particles per cubic or per centimeter as a function of energy. So you see Earth's radiation belts are really high density, but they fall off pretty quickly when you get to the higher energy ranges, where Jupiter, at the high energy ranges, it's the highest radiation environment we have in our entire solar system, Jupiter's radiation belt. So when you talk to Candy Hansen about the Juno mission come this spring, she'll be able to tell you all about the radiation environment at Jupiter, what that spacecraft, the Juno spacecraft, had to overcome to be able to operate in that environment, because it is really a killer, literally killer radiation environment. So suffice to say, we have a real mystery on our hands about Uranus's and Neptune's radiation belts. And with only one observation, is it even clear that what we observed is normal? Or is it just what we saw in that one instant of time, right? If they're really dynamic and really variable, how do we know that what we saw is representative of a long-term trend? And the last thing I'll mention, because I think some of you might be interested in planetary astronomy and atmospheric astronomy, there's this coupling between the magnetosphere and the ionosphere, what we call magnetosphere thermosphere, which is probably actually important at the ice giants, even more so than it is at Earth. And that's because it helps us with this mystery. The temperature of Uranus's upper atmosphere, or what we call the thermosphere, is hotter than expected for its distance from the sun. It's a bit of an energy crisis, if you will, that applies to all four of the giant planets. They all have thermospheres that are hotter than you would expect based on their distance from the sun. However, we've had more and more observations of the temperature of Uranus's thermosphere, and over the last 30 years, it's been steadily cooling, which is also somewhat weird because it should be maybe warming as Uranus gets closer to the sun. So this was a bit confounding. Like, is there some sort of time lag in how the thermosphere heats? The more likely explanation is that it's not the solar cycle. We've eliminated that possibility, and it's not the planet-sun distance, but that it's likely a long-term variability in the energy input from the magnetosphere, from plasma in the magnetosphere precipitating down and depositing energy into the upper atmosphere of Uranus. So stay tuned on that, because I think there's a lot of really great data we might be able to get even before we send Uranus orbiter and probe there, from maybe JWST, that will help illuminate in more detail the thermal properties of these planetary atmospheres, because it's an infrared telescope. The last thing I'll mention quickly is that magnetospheres are great laboratories for understanding a spectrum of magnetospheric dynamics, which may or may not spark your interest. Maybe magnetospheres are not for you, but a lot of people really love icy ocean worlds from an astrobiology perspective, or maybe you just loved 2001 Space Odyssey, who knows? But a lot of people love icy moon interiors and thinking about subsurface oceans beneath icy shells. And it turns out that whether or not you love the magnetosphere, it creates a great natural laboratory for studying icy moon interiors, because take Jupiter, our prime example, the 10-degree tilt between Jupiter's magnetic axis and its rotation axis, and the fact that the moons all cleverly orbit around in the ecliptic perpendicular to the rotation axis, means that those moons experience a magnetic wave. In other words, the tilt of Jupiter's magnetosphere creates a magnetic wave at the location of the moons. It actually creates a couple of magnetic waves due to some convenient harmonics in the orbit of the moon as well. And what those magnetic waves allow us to do is use a technique called magnetic induction to probe the interior, looking for conductive subsurface oceans. And we see that by an induction response. So just like when you walk through a metal detector at an airport, if you have metal on you, you're moving that metal through a Helmholtz coil, a coil of current that's creating a magnetic field. That metal creates a mini induction field from that as you walk through, and it creates a blip. It creates a signal that's seen in the current loop that is the metal detector. And so basically, when we fly by Europa, we see an induction field from this magnetic wave that's conveniently, almost to oscilloscope precision, being driven by Jupiter's magnetic geometry. And we see an exactly oppositely induced field at Europa, which tells us that there's a subsurface conductive ocean. That was one of the pinnacle discoveries from the Galileo mission as it was flying around Jupiter in the late 1990s, early 2000s. And it's the basis of the entire Europa Clipper mission, to go back to Jupiter and really study the interior characteristics of Europa as a potential habitable world. But this is not a technique unique to Jupiter, right? It actually totally stinks at Saturn, because the magnetic axis is perfectly aligned with the rotation axis. And it doesn't drive a very nice wave at all. It's perfectly aligned, and the moons don't see much of anything. But what about for these ice giants, right? The ice giants with these really complicated asymmetric magnetic fields, they're driving all sorts of magnetic waves at the locations of the moons. And the entire Trident Discovery mission proposal, which was very near and dear to my heart for about 2 years of passion project, was to try and determine, could we use that information we learned at Jupiter to remote sense, to magnetically sound the interior of an icy ocean world, to study the interior of Triton, which is a captured Kuiper Belt object in a crazy orbit around Neptune. And we wanted to know, because we only had a glimpse of it from Voyager 2, why Triton's ionosphere was so intense, even though it's so far away from the sun. And Triton, other than Io, was the first moon discovered to have icy plumes, cryovolcanic activities at the surface, as observed by Voyager 2 when it flew by. We could see them rising up and shearing off in the atmospheric wind and creating these deposit streaks at the surface. And so we wanted to understand the plumes, what was driving them, what was driving the resurfacing of the landscape, the fact that we would expect a cold, dead moon, and instead we get this incredible, refreshed, young terrain across Triton, even though it should be ancient. And then doing a lot of geochemical modeling and pressure modeling, considering the fact that could Triton be an ocean world, an example of a captured Kuiper Belt object that through tidal dissipation after orbital capture around Neptune had enough thermal energy dissipating that it could create and sustain a subsurface ocean in the outer solar system? Fantastic mission. Of course, sadly, the Triton mission was not selected in the last Discovery competition. We were down to the final 4 and they chose 2 missions, and they ended up choosing the 2 missions to Venus. But we learned so much during this mission proposal phase. We wrote literally almost 100 papers about everything we learned by furthering our modeling studies. And one of the coolest ones was just how can we use this complicated magnetic geometry at an ice giant like Neptune to magnetically sound the interior of Triton. And this is just an animation of Neptune's magnetosphere tumbling around its rotation axis and Triton on its highly inclined retrograde orbit. What does the magnetic wave look like at Triton? And can we fly by it and actually measure that induction response with a single flyby, which is what Trident mission was proposing to do. And this is just an idea of what that perfectly sinusoidal driving field looks like. And we have a couple of different fields summing together because we have 141-hour periodicity from Triton's orbit, a 14-hour periodicity from its relative motion, and the rotation of Neptune's field. And that little red line up there was Trident flying by and discovering an ocean in the outer solar system, which is sadly not going to be the mission that is flown. But it was a beautiful concept study that led to a really deep dive into complicated modeling techniques, not just inversions, but forward modeling and primary component analysis as to how you could really feasibly make these measurements and draw deep conclusions from them about the ocean interior. And I won't get into it other than to say that it's a beautiful study that not only tells us that we could detect an ocean, but that we'd be able to differentiate between an ocean and an ionosphere from a single flyby based on forward modeling of the induction response. And it's super fun science. So even without a mission, we could still get fun science out of a concept study for a mission. And we can use that to leverage that knowledge now as we're preparing for a Uranus orbiter and probe mission to go to Uranus and study Uranus's icy moons, which are potentially very interesting. We have Ariel, we have Miranda with its complex geology and geophysics at its surface, that there's just a host of mysteries to be resolved. And we can use what we learned from the Trident and Triton study to take this tumbling asymmetric magnetosphere of Uranus and look at the magnetic waves it generates at the icy moons and how we can leverage that information by flying by those icy moons and discovering if they have their own induction responses. And we've even done some preliminary modeling on that to make sure that based on the strength of those magnetic waves, we could actually detect that with our current measuring capabilities. So the dotted line is our threshold for being able to measure it with magnetometers, that we could fly there, and all of these different wave period frequencies are ones that we'd be able to detect if they were driving an induction response. So quick conclusions. I know I've thrown a lot of information at you about magnetospheres and icy moons and ice giants, but I think my conclusion in this is that I love Neptune and Triton, and I'm sad that we're not going with Trident to visit that magnetosphere. But the decadal survey pointed to Uranus as our next big target. And it provides such an incredible natural laboratory for the extreme edge of a dynamic spectrum of magnetosphere solar wind interactions that how can we not explore it? It's going to be fantastically terrific. And if we just look at it on the spectrum, we've got Jupiter, Earth, Saturn, Neptune, in terms of their increasing diurnal variations due to the dipole tilt and increasing seasonal variations due to the obliquity, to the extreme tilt of the rotation axis. And all the way over here at the top corner of that spectrum is Uranus. So it really is an end member within our own stellar backyard to study those extreme geometries and that extreme portion of the dynamic spectrum of moon magnetosphere interactions. So I'm excited to explore it, and I hope that we get there before I retire, because it's the long game to explore the outer solar system. And I usually end with this slide when I talk about Uranus and exploration, because it's a beautiful image. But we've got one better now, and that would be the beautiful image sent back by JWST of this isn't Uranus, actually, this is Neptune, because Neptune is close to my heart, but this is Neptune and a part of the spectrum that we have just not been able to observe it with such clarity. And JWST has provided this. Neptune looks dark because of the methane in its atmosphere actually absorbs infrared more than the high altitude ice clouds that are water ice, which reflect light in the infrared. And so you're seeing there the highlighting of those high altitude icy clouds above the methane atmosphere at Neptune. And what you see saturating, which is why it looks like this super bright saturating point, that's Triton and its icy surface reflecting all that infrared light from the sun back towards JWST and saturating it relative to what it was trying to observe. And it also had a chance, because of the darkness of Neptune absorbing that infrared light, it could really highlight and observe the rings of Neptune in a way that we haven't been able to do before. So I'll leave you with this image, and I'm happy to take questions until you're bored of talking about ice giants. And thank you again for the opportunity to speak with you all.
What did I just do?
Oh, that was me.
Sorry.
There's a couple of questions. There's a couple of questions in the chat. You can look at that now.
Yeah, I'm just seeing them now. I'm sorry.
Okay.
It was too hard while sharing to see them on the
Yeah,
screen.
sure.
So the second question, yes, JWST has looked at Neptune, and what I just showed you was the first public release image. They're going to have a lot more follow-up on this. They weren't quite ready to present this at the AAS meeting going on this week in Seattle, but we've been told that the timeline for that release is going to be sometime this spring, where they're currently, like, at this exact moment observing Uranus with JWST as part of the planetary component of the JWST observations. And so we'll get Uranus observations in a deeper dive. This image that I just showed at Neptune was, a public release that came out, weeks after it was taken. It was really short turnaround. They didn't do any deep analysis on it. They just wanted to get that image out to the public. And so there are droves of people working and doing deeper analysis on these observations now. So stay tuned. There will be so much more coming from JWST's capabilities within our own solar system, not just all the beautiful cosmic and galactic things that it can do. But there'll be a lot coming based on its observations of our own backyard as well. The other question, Jupiter's moon Europa, do we have an estimate of the radiation level at present in the subsurface ocean and implications for life? That's a terrific question. And the answer is, radiation is a blessing and a curse. Radiation for us is bad. We don't want to send astronauts to high radiation environments. We have incredibly strict limitations on lifetime radiation doses that astronauts can get, even beyond the shield of our atmosphere, which thankfully for us does a pretty good job of shielding us from the ultraviolet radiation and particulate radiation we would experience in space. At Europa, radiation giveth and it taketh. We're not going to see life on the surface of Europa. Even if it came up through a crack anciently, we're not going to find some DNA or anything on the surface of Europa, because the radiation would have destroyed it on very short order. Anything that would have been preserved on the surface otherwise. But radiolytic processes at the surface that cycle down into the ocean create important chemistry and energy sources for life within the ocean itself. And the ice acts as a shield from the negative impacts of the radiation. So it means it's hard to detect life at the surface. Even if it came up through a plume and landed on the surface, it wouldn't last there very long. Not just from the vacuum of space, but at a more fundamental DNA level, it would be radiolytically destroyed. But the products that it creates, the radiolysis products it creates on the surface that can cycle down into the ocean, are actually chemically and energetically very important for habitability. So it's a good thing in that regard. It just means that the life is going to be hiding underneath the ice shell, where it's safe from the negative impacts of the radiation anyway.
I have a question. Can you hear
Sure.
me?
Yes.
You were talking about, not being able to identify a potential plasma source, right? Neptune or Uranus. So what about the ring systems? Again, obviously they're not as complex or as dense as Saturn, but you have ring systems and ring arcs. Do they?
It's true. Yeah, I mean, at Saturn, we have a whole ring atmosphere and ionosphere. The rings are an important part of the plasma source. a fun fact is that Saturn's rings also absorb the radiation belt particles. So Saturn's radiation belts are the weakest and the most confined of any of the planets because of the fact that those rings act as really good absorbers of radiation particles. But it also acts as a source of plasma because rings get sputtered, material is scattered off of the top of them, then it becomes ionized. So they act as plasma sources as well. And it's a great question as to whether or not the rings of Uranus and Neptune also would create plasma sources. And we don't, oh, I'm sorry if you heard that. My dog is getting very hungry. She just baroofed at the door. It's an interesting question as to, can they are much finer rings, they're smaller rings, and can they create enough, oh kitty, can they create enough of a plasma source that would be the source of plasma in those systems? And people have been modeling this. We've been trying to see, like, based on the density of material in the rings, how much neutral could they produce, and how much ionization would occur from that neutral atmosphere, ring atmosphere, and would that be enough to feed the magnetosphere, as it were, create a plasma source for maybe the radiation belts? And it's really just such a complicated question. At Saturn, they absorb the radiation belts, right? Because the radiation actually is scattered and deposited on the rings, but yet they also create a plasma source, which then can be scattered by plasma waves and create radiation belts. So it's a bit of a conundrum as to what wins, the belts themselves absorbing the radiation or them being a source. I think the interesting question we're still going to have to battle is with this complicated geometry. It takes a bit of a space physics class to get down what magnetospheric convection is and why it enables stable trapping of plasma. But the symmetry being broken makes it very hard for magnetospheric convection to be a long-term stable process in these magnetospheres, at least further out. And then in the inner magnetosphere, the higher order quadrupole moments of the field, we think about dipole fields as kind of, this nice onion shape, right? Or, more than an onion, like apple core interior shape, and plasma bounces back and forth. That's how it gets trapped there. It's like your intro E&M magnetic bottle question. So the plasma is trapped there, but in a quadrupole geometry, like, does it get trapped in the little loops of the quadrupole? And what about when the quadrupole is rotating relative to the convection field from the solar wind? Overall trapping gets a bit more complicated when you don't have a nice symmetric dipole. And so there's a lot to study there. And we've got hordes of very energetic and ambitious grad students trying to use computer simulations and push the envelope as to what we can do to model these out. And we don't have what we're doing now is using theoretical studies to build up hypotheses tests that we can go and say, okay, we're going to test this hypothesis with the mission. We're going to make sure we measure X, Y, and Z with this mission, that we fly in these right locations, that we make sure we have sensitivity requirements on our instruments so we can measure these things and test the validity of these different hypotheses. Because when you're in the experimental or numerical experimental framework, you just don't know what the right answer is going to be, what the threshold is going to be until you get there and measure it. But they enable you to set the bounds on the experiment, which is critical when, it's going to take us a long time to build a mission and fly there. I really genuinely and not ironically hope that we get there before I retire, even though I'm working probably a third of my time right now trying to make sure this mission happens. And so it's a long game, and you want to make sure you send the right instruments and have really well-defined tests to answer these fundamental questions. So I can tell you we're working on it, and I can tell you that there'll be a lot of papers out about this, really refining and defining the questions we're trying to answer before we even get to the launch pad.
I have a question.
Yeah.
And a comment as well. I love the fact that the Voyagers brought you to where you're at. You never know what sparks that interest, right?
It's true.
Yeah. And one question I had was about when Voyager, you said, went through the one pass of Neptune and you found no radiation. I mean, and I have a cat on my lap, so I couldn't take notes. So,
I understand.
So I might be getting the facts wrong, but was that when the Voyager went bypassed Neptune, you found little or no radiation?
It was almost that. We found very little plasma. It was
Plasma.
very, very low
Yeah.
density plasma. They still Neptune still has radiation belts, and those are really confined to the inner magnetosphere when we went the closest to the planet. But they were not very intense.
Where was Titan in it? Where was Titan in its orbit around the planet at the time?
Oh, Triton. I'd have to go back and look at where it was in its
Yeah.
orbit. We flew, I mean, the images we have of Triton, which are beautiful, right? And they gave us these images of those plumes and the plume tracks and the cantaloupe terrain and all this fantastic surface detail, which when you think about it is actually incredibly coarse resolution, because we were tens of thousands of kilometers away with Voyager 2 era cameras and data rates. But we were still able to resolve all that detail. I'd have to go back and actually replot out where Triton was in its inclined orbit. It's in a very inclined orbit, so it's not, we didn't go very close to it. We would have loved to have gone much closer, which is why we never got to measure the magnetic field and see if there was an induction signal or an ocean. We were nowhere near close enough to it to measure that effect.
What would ever happen if, because I know the sun changes its polar north and south, every 11 years, whatever.
Yeah.
And I heard that Earth might be doing that as well. What would happen to all your studies if that flipped?
At Neptune? Well, it's a great question. We've actually thought about this a lot. The dynamo theorists, the people who study internal dynamo generation, feel very strongly that at Neptune and Uranus, the dynamo is generated closer to the surface in a superfluid layer. And that is the reason why we see such strong higher order or higher degree magnetic moments, the quadrupole and octupole terms. So initially it was posed, well, maybe we flew by both of them when they happened to be going through a magnetic reversal, which, two of them at once. I mean, our magnetic reversals happen very infrequently, and that would be pretty remarkable unless we break our template a bit and realize that the magnetic fields of these ice giants are not generated in the same way that they are at Earth or at Mercury or at the giant planets at Jupiter and Saturn either. And that is why we end up with such higher order moments. And there's a very high likelihood that when we go back decades and decades after, that those higher order moments will have changed. I mean, our own higher order moments at Earth have changed in my lifetime. The South Atlantic anomaly is actually over South America, not the South Atlantic anymore. And our pole has moved significantly even over, the 40 some odd years of my life. And so we know those higher order moments change at Earth. And I think with Neptune and Uranus, with the source of the dynamo field being closer to the surface and in a more unstable region, that we'll likely see, if I were a betting person, I would bet that those higher order moments, which generate the off-centeredness of those fields, will have changed significantly since we flew by with Voyager. And hopefully we're planning on flying by a lot closer to really resolve them in a much better way. I hope that answered your question.
Yeah, sure.
You've all been asking great questions, and I hope I'm capturing them.
Sure.
Thank you for the kind comments in the chat as well.
I have a quick question.
Sure.
Maybe, I don't know. I'll ask it anyway. I'm a little older than you, but I was very much caught up with the Voyager mission and the visits to each planet. What I recall when we passed by Uranus was that it seemed to be very quiet compared to the other Saturn. Ouch. I'm not talking to you. In comparison to Saturn and Jupiter. We kind of if I recall, we kind of threaded a needle. We went through because it's on its side, right? We kind of went through it. So it's going to be the same thing again when we get back there, right? But this is supposed to be staying, right? The Uranus Clipper.
And the Uranus orbiter and probe will be in orbit around
Yeah.
it. So we'll get to see all of it. And in theory,
How do you get
we should be
into
getting
that?
there at a different season? You know, we flew by right at solstice for both pretty much Uranus and Neptune with Voyager. And so we'll likely, depending on very many factors and how hard we push at NASA with OPAG to get our launch date when we want it to be, getting there at a different season to study the magnetospheric dynamics at another part of its seasonal obliquity phase. But in terms of the atmosphere and what we can see when we're in orbit, that will be nice because closer to equinox, you get to see the whole atmosphere, whereas at solstice, only half of the planet is illuminated because the rotation's pointing at the sun. So the summer season is getting all the sun and the winter season is getting none of the sun for a lot of decades. It's really phenomenally hard to wrap your head around, actually.
And the launch date, you're hoping for 2020.
Oh, no, 2024 is when we start what we call phase A, which is when people will start saying, we want to put these instruments together and glue them on the spacecraft. And then we get years and years of developing the instruments, building the instruments, getting them through all the different phases to getting to a launch in like 2038.
And arrival?
Later.
So
Outer planets is the long game. It's not for the faint of heart. It's a very long game, and it's a less long game for Uranus than for Neptune, which was part of the risk factor that also weighed into them deciding when we would go. And actually, and I don't quote me on that, I might have that wrong. We might be pushing for a faster development period to get us off closer to 2032 or 34, and then the cruise is about 14 years to get to Uranus. 10 to 14, depending on how big a rocket we go on and what our exact trajectory is, and if we can use some of the more modern boosts, if you will, to get there faster. And that's a complicated trade. You can always get going faster, but then you need to be able to slow down enough to get into orbit. So it's not just a matter of getting there fast, it's then how do you slow back down to get into orbit, to get to have orbital capture? And that's another part of the equation in terms of how you balance how quickly you can get there with whether or not you can get into orbit. It's a great aeronautical engineering homework assignment to ask students.
And when are you retiring?
Not for a while. I've got some decades left on me. It'll be fine. And, planetary scientists, even when we retire, we don't really retire. So, it keeps going as long as there's a will. You just don't have money for it. But at that point in life, who cares? It's just money. So no, we retire so that the next generation can come up and get to do all the good stuff. But almost all of the folks that I'm fortunate to work with and learn from would be retirement age if they wanted to stop doing what they're doing, and they're just going on and doing it anyway, which is one of the great blessings of planetary and astronomy. All these great things is they get these outer solar system missions and these big missions, even like JWST was so long in the making that it's really, we don't think about JWST as a mission because it's a telescope, but it's really a generational mission in terms of conception through building, through launch, through usage. It's generational, and that makes it a really fun thing to work around.
Great
Any
presentation.
other questions?
thank you.
Thank you all
Very
so much. And if
Oh,
you
yeah.
happen to be driving by Bryn Mawr or Haverford, give them a wave for me. I miss those beautiful campuses and that beautiful area so much.
Thanks so much.
Thank you all. And have a good evening.
Thank you.
You too.
Cheers. Bye-bye.
Bye.
Bye.
Hey, Kathy.